Okay, good morning. Welcome to the second episode of this DSC Innovator webinar series, where we explore the tools and solutions shaping the future of district heating and cooling. Just for information, this series of webinar brings together innovators, research and industry practitioners to examine emerging approach that can accelerate decarbonization, improve planning, and also support smart investment decision across Europe thermal networks. My name is Gabriele Pesce. I'm the Director for Innovation at Euratom Power, the District Heating and Cooling International Association, and I coordinate also the DSC Plus platform, the R&D branch of Euratom Power. Today, in this episode, we're going to focus on a structured mapping framework for thermal sources and loads in district heating and cooling system presented by EURAC. Let's say by combining GIS-based analysis of heating and cooling demand, wasted potential, and local renewable energy sources, the framework provides a comprehensive, spatial, and quantitative foundation for strategic planning. Before giving the floor to our speaker of today, I would like to give you some practicalities. So the webinar is recorded. So after this will be freely available on Euratom Power social channel. And also you can, and I really suggest to do that, you can post questions through the Q&A box you can see in the bottom of the Zoom application. So of course, I really suggest let's make this webinar quite interactive. So you're really welcome to pose any kind of question you wish to pose to Andrea. So without further ado, I would like to give the floor to Andrea Menapace, our guest of today, and to introduce the topic of today's webinar. So Andrea, please, the floor is yours. Thank you.
Thank you very much for the nice introduction. It's a pleasure for me to be here today to the Innovators webinar series. I'm Andrea Menapace. I'm the coordinator of the district heating and cooling team in EURAC at the Institute for Renewable Energy. And today, as introduced by Gabriele, I'm glad to present the GIS-based mapping approach that we developed in order to map the thermal sourcing and the loads for district heating and cooling systems. This work started within the Life for Heat recovery project, was further developed in HeatMineDH, and finally refined in the current going on DHC SwEEtch. It has since been applied in several cities with diverse urban and energy contexts. This approach allows to define the spatial identification and characterization of waste heat, local renewable energy sources, and heating and cooling demand within the area of interest. Okay, here we can see the outline about today's presentation. And I will start with the context and the motivation behind this framework, and I will introduce also an overall structure of the tool. After that, I will move to the three core layers that are heating and cooling demand, waste heat, and local renewable energy sources. Finally, I will summarize the main findings of the proposed mapping framework in the conclusion. So let's start with a bit of context. District and cooling systems in Europe are undergoing a structural transformation. Under the revised energy efficient directive, we know that the definition of efficient district heating and cooling is progressively evolving according with an already defined path. In the short term, high efficient cogeneration play a central role in meeting these heat efficient targets. However, the regulatory trajectory is clearly shifting. While combined power remains relevant in the transition phase, the long-term targets increasingly prioritize renewable energy and waste heat integration. In fact, we can see after 2040, combined power, high efficient combined power no longer counts as a standalone requirement, and compliance is primarily driven by renewable sources and recovery energy. This means that this heating and cooling system must progressively move from fossil and CIP supporting configuration towards supply structure dominated by renewable and waste heat. Structural shift requires forward-looking and strategic planning, and this is the context in which the mapping framework has been developed. So these regulatory and strategic challenges are the main drivers behind the proposed framework. At the core, there is growing regulatory pressure to comply with the revised Energy Efficient Directive, as previously said, and the Renewable Energy Directive too. Meeting this requirement is not only a matter of adapting a few parameters, it means addressing increasing technical and operational challenges as systems must progressively reach high efficiency and renewable energy thresholds. At the same time, cities and operators are required to move towards structural urban heating and cooling decarbonization planning. This implies a comprehensive transformation, meaning modernization network, integrating renewable energy and waste heat, improving production efficiency, and in many cases, expanding the network in new areas. Looking for the new opportunities in the urban context. So also effective decision making becomes critical. Planning cannot rely only on assumption. It requires structured and robust procedure, including systematic sources mapping and assessment, district modeling, scenario analysis, feasibility study evaluation, and finally, investment planning. And at this step, all these steps depend on having a clear and quantitative understanding of the energy context in a defined area. That means that it's essential as first step, the mapping. So identifying and characterizing the energy context provide the analytic foundation for what are the next step. Okay. So here you can have an overview about the 3 layers proposed in the GIS modeling framework. So the approach relies on a structural GIS-based analysis to map the local energy context, providing an approximative estimation but comprehensive and qualitative screening of all the available options. So the first layer is heat and cooling demand to define the spatial distribution and the thermal load, both within the existing district system areas and also in potential expansion zones. The second layer focuses on waste heat. Here we identify industrial and tertiary waste heat sources, characterize the energy potential, temperature level, and temporality for be considered to be included in district networks. The third layer addresses local renewable energy sources, meaning mapping, for example, solar thermal and ground sources potential within the urban boundaries, analyzing both the available area in which we can install renewable sources and a rough estimation about the supply potential. In the next slides, I will go through each of these layers. Okay, so let's start from the fourth one, that is heating and cooling demand. The objective of this, of course, is mapping, but also characterize from the temporal point of view the heating and cooling demand of the analyzed urban area. We distinguish between residential and non-residential buildings, applying different energy density benchmarks in order to estimate the final yearly demand. the estimation combine different kind of data that we can give a look in detail later. So the result will be a spatio-temporal dataset at building level. Okay. I don't want to enter too much in detail, but just to give you an idea what are the required inputs for the estimation of the demand. So fourth are building characteristics, as you can see, such as footprint area, number of floors, building use, type of buildings, and construction period. Second are the climate data, specifically temperature and solar radiation. Third, we base our calculation on two energy density benchmarks that are derived from INSPIRE and from HotMass for non-residential buildings. And finally, when available, we can include also metric consumption data in order to refine our estimation and also the hourly profiles. On the right, you can see a simple example about the GIS inputs with the related table with the already mentioned information. Okay, so a bit about the calculation. So mainly we apply a two-step procedure in which first we calculate the annual heating and cooling demand at building level using a query of two databases, INSPIRE, in the case of residential building, in which we have as inputs climate zone, building topology, construction period, and set point temperature. Instead for non-residential building, we use HotMass density. Annual demand is way defined, but we have a few correction factors that allow to better refine the estimation according with the local context. For example, we can apply a bias correction on the net floor area, on the local climate condition, using degree days, and when available, we can also use some metric data of a sample of building, for example, for calibration. Second step is to reconstruct the hourly demand profile. That is, as you know, is quite important to be used in simulation in order to have a better understanding about the system and how to implement the different sources and meet the demand profile. In this case, we use the degree days in order to better profile the demand along the year, and then we refine the daily pattern according with some stochastic analysis. And in case of available data, metric data, of course, we use also that data in order to better provide a better hourly profile of the typical year. The next slide, we can see the output. So two main output. First, the reference map of the all buildings in the selected area with associated annual heating and cooling demand expressed in megawatt per year. This allows a spatial visualization of the thermal density and allow us to identify and prioritize future network expansion area, for example. Second, for each building, we generate an hourly demand profile covering both heating, cooling, and domestic water demand. Tabs are delivered in a structured GIS format file and are directly usable for creating scenario with a dynamic model. In short, the demand mapping provides both spatial resolution and temporal detail, and although the results are model estimated, they offers a robust indication of local demand pattern, especially when calibrate with, of course, available measured data. Now, let's move on the net layer. Object is to map and estimate, in this case, the wasted potential within the area of interest. The methodology adopts two complementary perspectives. On one hand, industrial sources covering manufacturing activities such as dairy production or metal works, for example, and many others. On the other hand, the so-called urban sources, including tertiary activities like hospital, supermarket, swimming pool, ice rink, data center, and so on. Industrial sources often provide medium and high temperature heat to recover. Instead, for tertiary activity is always low temperature heat to be recovered and then to be integrated by the use of heat pumps. Let's move to the inputs. Also in this case, we have different kind of inputs. I don't want to spend too much time, but just to highlight how our framework relies just on easy to find information. In this case, for industrial sources, we start from a list of facilities typically provided by the Chamber of Commerce, including the location, NSAA code, and size that are expressed as number of employees. Then NSAA code is the European classification system for economic activities, and it's essential in order to be linked to different industrial processes that allow to estimate the heat recovery factors. Sometimes the number of employees can be also critical because it can be that one company has more than one site in a city, and so we need to take care about this potential technical issue. This information is then combined with statistical data from the Danish reference database, which links industrial sector and size to waste heat amount at defining levels of temperature. Instead, for urban sources, we adopt a semi-mathematics-based procedure using OpenStreetMap, Google Earth Service, and digital survey models. This allows us to identify building footprint, number of floors, and activities types that we link to some literature-based coefficient in order to have an idea about the waste heat to be recovered. So to sum up, both methods merge geospatial data with literature factor, and in the next slide we can see how we can use this data in order to do our calculation. So on the left, you can see that for industrial sector, we use the Danish reference database, as said before, with link the sector with number of employees and provide the available waste heat at low, medium, and high temperature. Company size strongly influences the potential. We apply piecewise linear interpolation on the number of employees in order to have a more precise estimation about the available waste heat, not just for category, but with interpolation. On the right, you can see that what is the different methods for the urban sourcing. Here we focus on specific building categories, such as already said, supermarket, for example, or swimming pools. The waste heat potential is calculated based on building footprint, number of floors, and literal-based recovery coefficient. On the bottom, we can see an example of the meat production, in which we can see the waste heat according with the different size, increasing with the increase of the size of the activity, and for the 3 levels of temperature. In the next slide, we can see an example of waste heat output. The output of this process is, as you can see on the left, a map of industry and the potential heat recovery for each industry. Of course, there are a lot of potential activities that need to be processed, and on the right you can see the screening that we apply for a case study in which, for example, we select a minimum threshold of 1 gigawatt-hour per year and a maximum distance from the existing network less than 1 kilometer. It allows us to prioritize sources that are technically useful for integration into district cooling system. In addition to thermal value, also in this case, we provide a hourly profile for each selected source, making the result usable for modeling purpose and scenario preparation. So also in this case, outcome is not just a map, but as for the demand, a structured database of spatial and temporal waste heat potential. Let's move on the third layer, one of the renewable energy. The object in this case to identify available areas and provide a preliminary quantification of the renewable heat sources that can be installed in those areas, and later on to be evaluated the integration in district heating or cooling networks. In this case, we focus on two main categories. For solar thermal, consider both rooftop and ground monitoring installation, and second, ground sources, including shallow geothermal and deep geothermal, if relevant. We first identify suitable area, taking account land use, constraint, and proximity to the existing network. We can estimate the technical potential using literature-based performance parameter and simplify engineering assumption. The goal here is to obtain a spatial resolve and quantification indication of the renewable potential available at the urban level. Okay, also in this case, I will propose the inputs of this analysis. So also in this case, we will not grab a lot of information because the purpose is to provide broad information for the planning to be later on deeper if necessary. So first, the geographical definition of the site is needed, including the existing and potential district areas. So it's important to know also where the existing network is located. Second, available installation surfaces that are defined through the GIS calculation using OpenStreetMaps and or Urban Atlas to filter and exclude protected or restricted zone. The idea is to define a few areas of interest that on which to calculate the available potential installation of some sort of renewable energy plant, and to be later on to take in account in the process of planning. There are other information that can be connected as the temperature of the network, the geological condition, the environmental constraints, and so on. On the right, some example about input. I would like to move now on the method. For time reason, I will focus only on ground source example, just to give an idea how the methodological logic apply to the renewable energy mapping layer. So I would like to stress that in this case, it's really a rough estimation intended as a first level technical assessment that provides just an order of magnitude of the potential, and in case of interest from the operators to be included those sources in the scenarios, energy decarbonization scenarios, need to be better investigated. So methodology in this case start with the identification of suitable areas, mainly not built zones and available urban areas, excluding, of course, any restricted areas. Then we estimate the available water flow of, for example, an aquifer well based on a specific extraction rate per unit surface. From that, we calculate the thermal power at the source side using standard thermodynamic relations. And of course, if the temperature level is low, we can also do a calculation including a heat pump in order to have the final available thermal power. This allows us to have a preliminary idea about the potential of renewable energy, with also an hourly pattern of the different sources. Now I will show you just a few examples. On the left, you can see the thermal potential estimated from aquifer wells. You can see that we analyze mainly the area close to the production unit of the distribution of this specific district network, because the intention is to make also easy the integration in the distribution system. And and it provides a preliminary analysis of the potential to be included in those specific area. On the right, instead, we can see just an estimation of a thermal solar on the roof of an industry that we also consider for other case studies. Of course, also in this case, quite important to apply a profile in order to be better used in the following analysis. I'm close to the end. Okay, here it is the final slide. So to conclude, the mapping framework acts as a strategic planning tool for district heating and cooling decarbonization. It provides a structured risk-based assessment of both demand and supply, integrated three key layers that are, again, heating and cooling demand, waste heat, and renewable energy sources. This approach enables spatial screening and quantitative annual estimation, along with the hourly profile that ensure both spatial and temporal consistency. The output are directly usable for modeling activities and scenarios development that will be crucial for decision-making process about the decarbonization strategy, and of course also to be taken account for expansion planning. At the same time, it facilitates the alignment with the evolving directive, and in short, this is what the framework can provide. So an important support, in my opinion, for the decarbonization strategy, even if a first step, of course. So it's all on my side. Thank you very much for the attention, and I will be glad to answer any question.
Thank you very much, Andrea, for this very interesting presentation. And just as a reminder for the audience, the slides will be available for the participants. I think this kind of projects are very, very important for the future of DC heating and cooling. Just as a little reminder, according to some recent studies, just waste heat could potentially cover all Europe's heat demands by 2050. So this kind of project, these frameworks could support also public authority to really exploit the potential of the renewable waste heat they have in their territory. So thank you very much, Andrea. For the audience, a reminder, you can post questions to Andrea through the Q&A box in the bottom layer of the Zoom application there. So don't be shy, I will read it for you. In the meantime, waiting for some questions for the audience, I have some questions for you, Andrea. So I hope to inspire the audience as well. So let's start from data qualities and also planning risk. So we saw that your framework relies heavily on benchmark data sets, for example, Inspire, Hot Maps, Danish database, literature, and so on. How sensitive are the results to data inaccuracies? Because can be, what is the margin of error municipalities should assume before making investment decisions? So we know that there always could be some marginal error. So how sensitive are the results to this framework to data inaccuracies?
This is a really interesting question and relevant because, of course, quality of the data is quite a critical point, and we know that grabbing data is, even nowadays, if we are in the era of big data, is quite challenging. So there are a lot of restrictions, and for that, our mapping approach is based on most of the time on really easy to find data and open source data. So any can collect easily for any case studies. Okay, come back to the question. Of course, our calculation, especially the demand one, are rely on benchmark datasets like Inspire and OutMap. We know that those benchmark are based on quite nice bottom-up modeling approach. So we can rely on that, but we know also that they have some drawbacks because maybe they cannot be specific on each area of the world. So of course they can be refined. In this case, for that, we use some correction factor that allow to better fit in each single context and allow to have a better estimation. Later on, the best case is when we have also a sample of buildings that are measured, so we can have real data. If we have those information, of course, we can refine even more the result and the outcomes of the modeling approach. And in this case, we can have really fine results. This step can be done also in a second step if needed, if we don't have the data at the starting of the analysis. But yeah, so to conclude, I think that the result, especially of the demand part, is quite consistent. Maybe regarding the cooling estimation, we need to improve a bit the methods because we know is rising the importance of this energy demand, and is also more complex because there is the internal human behavior to be considered, the gain of the radiation, so it's a little bit more complicated, but we are working on that. Nevertheless, for the rest, I think that we can believe on the results, and I think that are quite reasonable. Of course, we know there are several other sources of uncertainty that can affect even more the calculation, like the number of inhabitants that can be changed a lot in the long term, the change of activity, but also the change of technology, maybe.
Of course, Andrea, it's totally reasonable. Okay, thank you, Andrea. We have a first question from Rita. So I will read it. Will the tool be openly available? And how could, for example, a municipality use the tool? Is it available for all European territory?
Okay, so good question. Right now, the tool is not open, but and right now we always use internally the tool to provide to municipality the results. For example, we have applied this tool in several European live projects that we know that are quite applicative. And so we really work with real data in different contexts, different part of the Europe. So yeah, definitely we can apply to any location of the world without any problem. The data that we require are quite straightforward to collect. So maybe sometimes we need the help of the local stakeholders or operators in order to have maybe the metadata, but for the rest, I think that there is no problem in applying anywhere. Right now, instead, is not an open source tool. We are thinking about that. What we need a bit of refining some part, especially the user interface.
And one day it will be available, or for you?
Honestly, is a question that I cannot answer now, because it's not just up to me, but it's up to also the strategy of the resource center that is really open on these kind of questions. We have several open tools, but we need to discuss one by one if it's possible or not.
Totally understandable. Thank you. Okay, we don't have a question, but more like thanking. Thank you very much to organizer and presenter. Thank you very much. The subject is really crucial for EED and RED compliance. Absolutely, as I said before after the presentation, this kind of tool are pivotal to really make this scenario of decarbonization real, and we can do it, of course, even though still heating and cooling relies too much on fossil fuel. This kind of framework really helps accelerating the transition. Thank you, Peter, for your nice word. Then an anonymous attendee. So don't be shy, I'm kidding. Is there a research paper about this work, and probably where we can find it if it's open public?
Yeah. Unluckily, the paper is under review, so I hope that it will be available sooner. But right now it's not available. But if you are interested, you can contact me via LinkedIn or by mail, and I can share you in advance some information.
Concerning that, Andrea, do you have a slide where we have your email contact, or?
Yeah. The last slide there is all my contacts.
Can we go back to the slide so people can maybe write down your contact?
I cannot right now.
Marietta, can you go back for the last? Okay, no, right after probably.
No, it's the last one. The thank you slide. Yeah.
No. Okay.
It's not a slide. There is just a link on our. So in the PDF version, you will find the connection to, but not here. Sorry, but I can put in the chat if possible.
Yes, please. Thank you very much. Perfect. Thank you. So people can see it. Okay, waiting for hopefully for other question. I still have some. So Andrea, from screening to bankability, I think it's a very important topic. We saw that the framework enables special screening and annual hourly estimation. But at what point does this move from strategic planning to something bankable? So what additional validation steps are required before operators can rely on it for CapEx decisions? If I'm clear.
Yeah, a clear question. Unluckily, I didn't put in the presentation a slide about the entire process that usually I do, but this webinar is dedicated to mapping, so I didn't include the full steps to develop the compensation plan. Of course, as you said, it is just the first step, the first analysis. is crucial because we need to know the context, the energy context on which we have to operate in order to decarbonize a city or a district system or a district. So it's important to have those information. The step later is to discuss, assess the reliability of the information that we collect with operator stakeholders in order to evaluate if those information are correct or not, or maybe a waste heat connect with an industry is not open to deliver to the district system, for example. So a lot of things, a lot of information need to be assessed. Later, of course, when we define better what is significant and what is not for the planning procedure, we move to the modeling part. Of course, we know we need to meet the demand that is changing in time, so it's crucial. And we know that also renewable sources are quite unpredictable many times and are also variable along the days and the seasons. So it's quite important to have an hourly model to build up the scenarios. When we have the scenarios, need to be defined the goals to move to the final assessment and the feasibility study, and just finally the investment plan comes in, and so also bankability. So it's a long process starting from the mapping, but of course we can see a lot of good example in European project. For example, the projects that allow us to refine these methods that I present today is life districting DHC SwEEtch that is related to this chain. That's a chain starting from mapping, ending to investment planning on real case studies. So yeah, your question is quite good, was really good, and yeah, there is a long process to be done.
Absolutely. And also, this reminds me that the fact that we know that bankability of district heating and cooling projects is one of the most important fundamental topic nowadays, because we need to leverage more private capital. And unfortunately, we know that district heating and cooling is perceived still as a very risky infrastructure in the long term. So this kind of tool can also reduce the risk for investors in taking these investment decisions. So not just the supporting transition, but also supporting more private capital investment in our sector. So once again, I think we want to underline the importance of this kind of project and research work. I don't see any other questions, so I can keep on roasting you. Also linked to the first question to, let's say, potential inaccuracy of data just because of the changing framework and so on, the long term and so on. We know cities are not static. Beyond the increase of inhabitants or population, we also have different renovation rates, the electrification of the heating sector, and not just the heating sector, building efficiency improvement, and also, as you mentioned, with cooling, behavioral changes. Of course, all that can dramatically alter demand of heating. How does the framework you're developing account for future uncertainty in demand projection, especially on the long term, like towards 2035 and 2050 targets?
Well, thank you for this question. Yeah, you're perfectly right. We are in a really dynamic context. There is climate change that is pushing us to change quickly and to apply quickly this energy transition. So on one side, we have the climate condition changing our urban environment, making more challenging, for example, the hot waves and so on. On the other hand, we have the need and quick improvement of the technologies, and that can, of course, affect a lot the demand, because energy renovation, for example, can decrease the demand of heat in the future. So how to manage that in the demand mapping, for example? In true, it's just a question of provide the right inputs. For example, usually we use the temperature radiation of the typical year, but if we want to apply the framework to a future reference year like 2050, we need to fulfill in the mapping framework the climate scenarios of that year, and of consequence we will have a different demand for heating, cooling, and so on. But of course, I think that the second part is more challenging, because of course to know in advance what could be situation at long term about the new technology that will be installed in a city, or the new building, houses and so on, is much more complex, because depends of a lot of factors like incentives, the economic growth of the places and so on. So more difficult, but also in this case we can do some hypotheses, for example, of percentage of building that will be renovated, for example, and to include this in as a characteristic of a portion of our building stock. It is an example in which we can try to include those dynamic that, of course, are ongoing at the urban level. Of course, depends a lot on the input that we need to prepare, and we need to define according with some hypothesis on how will be the future of the city.
Of course. Thank you, Andrea. And linked to this question, also concerning industrial waste heat. Your methodology estimates potential based on sector data and employee size. So again, how do you address, for example, operational variability, industrial relocation risks, or also confidentiality constraints when translating theoretical potential into secure long-term supply? Because we know that waste heat supply on the long term is one of the biggest risks in waste heat recovery. So how your framework can deal with this?
You touch a really critical point.
Today we also want to challenge you also. So let's speak about that. And of course,
what is perfectly fine. We define this available waste heat as potential, because need to be evaluated properly. The first analysis is just to understand the potential, and most of the time utilities are just interested in the largest one, because of course small one are not so of interest, because require a lot of steps before to make it feasible to be used. So one time that you screen and select just a few interesting cases, of course you need to start some analysis, and especially to meet those companies to understand, first of all, if these wastes exist, because could be that there is the same category of company, but it's not going on exactly the same process that are defined according with the standard definition of this sector. Second, how large is the waste heat already recovered from themselves, because could be that a well-organized company already use part of the waste heat internally. And third, need to find an agreement, of course, not easy. And it's just to understand if the process is feasible. Then there are all the part of the risk that, of course, we don't know the company in the future what if we will still working on the same sector, if maybe it will close the it will not anymore operate in the future. So it's quite a critical analysis. So I think, for my experience, that case in which there is a double interest from both sides are much more interesting cases, because of course the company could be a prosumer, for example. So in this case, maybe can be much more feasible to going on with the study and the agreement. And but for example, just to change a bit, actually we are working a lot using waste heat from wastewater treatment plant. Why?
Mm-hmm.
For this reason, because of course they are there and will there forever probably, because the process will never end. And of course, company are prioritizing really stable waste heat, and not related to industries that can be not present forever in the future.
I know was not an easy question, but you tackle it super well. So, thank you.
Thank you.
Okay, we are almost running out of time, so maybe just one last question, maybe more open, so you can you can relax. Well, maybe we never touch upon the solar geothermal integration, so we always speak about waste heat and so on. So maybe one question on that. So for geothermal and solar integration, your approach identifies technically suitable areas. So how does the framework incorporate also social acceptance or land use competition, permitting complexity? We also know it's quite an important topic that, could become real barriers.
Yeah. Okay. In this case, the framework tool just provide some options.
Mm-hmm.
So we take in account what is available. So, for example, areas that are not permitted to install any kind of system. So we can exclude some natural area, or this kind of constraints, or any kind of constraints that are available. But of course, later on, we cannot go in deep as you asked me, because of course it requires other kind of processes that cannot be done with a tool, I think, but can be done with long process of involvement of people, stakeholders, and so on. So yes, let me say, we can just identify a potential area to be discussed later on. It is my
It's
answer.
an iterative, let's say, process. Of course, I understand that the mapping framework is a tool, it's a technical tool, and for its nature, some technical constraint. And then, of course, when we go on the field, we also need to speak with people and with stakeholders, industries, public authority. Of course, it's not that simple. I completely understand it. It's more than normal. Absolutely.
No. Just to do a last comment. Yes,
Sure.
based on that, we can build several scenarios that can be put on the table and discussed later on. So most of the time, some of these scenarios are deleted just for this kind of reason, because are not feasible. There are some constraints that we don't know, social problems. So yes, allowed to have a plethora of scenarios that later on can be discussed.
Exactly. So the framework and supporting decision with, like, say, a flexibility of analysis
Yeah.
from the people using it. Of course, we are no robot. Okay. One very broad last question. So, as I'm a policy guy, so I think we need to touch upon of the ED and RED three targets. So, do you see this mapping framework, as a compliance tool or as a strategic transformation instrument? Can even reshape how cities design the thermal ecosystem, let's say. So just a compliance tool or really an instrument for transformation?
Good question. I think that is more a strategic tool because the normatives, the EU directives are just the reason why everyone now is looking for some new solutions. But of course, can be exist also without directive. Of course, directive is the driver that allow to move through the decarbonization. But I will define more like a strategic tool because allow to map the energy opportunities that are around a city, and mainly it is the rule of the tool.
Absolutely. Thank you for your work, Andrea, and to your team working on this. Thank you, Andrea. It was really nice to talk with you. I hope we inspired the audience in this very sunny Wednesday in Brussels. I hope the same in Italy. And where are you from? All people. So maybe before leaving you, just a couple of reminders. So Euratom Power is organizing again the biggest district heating and cooling related event in Europe from the 9th to the 11th of June 2026 in the beautiful city of Kraków, Poland. Polish market is it's very interesting, and of course it's a city full of art and a beautiful city. So 500 more participants, a lot of session, more than 80 speakers, and 30 more and 35 exhibitors. So I really suggest you to register also because we could benefit from the early bird fees. So we're waiting for you all at the in Krakow for the Euratom Power Congress. And that's not all. Of course, the DSC Plus webinar series on innovators keeps on going. Next week on the 4th of March, we're gonna talk about distributed thermal energy storage, and again on the following week, on the 11th of March, we're gonna speak about evaluating embodied carbon in heat network projects. And these are just the next two episodes, and other are coming up. Thank you for following us till now. Thank you really much, Andrea, for your inspiring presentation. And I wish you a beautiful rest of the day. Bye-bye.
Bye.